Hey everyone, welcome back. I am absolutely thrilled to have you here for today's explainer. Today we're diving into the world of chemical kinetics. I want you to think for a second about the difference between a piece of iron slowly rusting over years versus a log of wood catching fire and burning up in seconds. That massive difference in speed, that's exactly what we're looking at today. We're going to start by measuring those big, observable, macroscopic reaction speeds, and then we're going to shrink ourselves all the way down into the microscopic, high-speed chaos of molecular collisions. It's a totally fascinating ride, from macroscopic math straight down to microscopic reality. So let's get started.
Okay, let's set the stage by establishing our core premise. You see, in chemistry, thermodynamics is the branch that tells us if a reaction is even going to happen at all. It deals entirely with the start and end energy states. But here's the catch. It tells us absolutely nothing about time. And that is exactly where chemical kinetics swoops in. Kinetics is literally the science of change. It's entirely dedicated to answering one really critical question. How fast?
Here is our quick roadmap for today. 1. Defining reaction speed. 2. The math of change. 3. Variables that control that speed. 4. Microscopic collision theory. And 5. The master synthesis.
Let's jump into Section 1, Defining Reaction Speed and How We Measure the Change.
When we want to track a reaction's speed, we're essentially looking at the change in its concentration over a certain unit of time, usually measured in moles per liter per second. And as you can see here, we can actually look at this from two different perspectives. Over on the left, we can monitor reactant depletion. See how the line curves downward as the reactants get used up? Notice that negative sign right there in the formula? Well, because the concentration is dropping, the change is technically a negative number. So we simply add a negative sign to the equation to make the overall mathematical rate a positive workable quantity. Alternatively, over on the right, we can track product formation. Here, the line curves upward as brand new products appear, which gives us a naturally positive rate. Both of these graphs are telling the exact same story about the reaction speed, just from two different sides of the coin.
Now this brings up a very real-world problem we run into, which is brilliantly illustrated here. Take a look at this curve showing the hydrolysis of butyl chloride. The reaction doesn't just happily cruise along at one steady speed. It physically slows down over time as the reactant concentration starts dropping. If we were to just take the average rate, which is that straight green line connecting the start to the end, we completely miss what's actually happening. And that proves exactly why calculating the instantaneous rate is so incredibly crucial. By taking the tangent at a specific point in time, like in that zoomed-in circle, we capture the ever-changing reality of the reaction speed at that exact specific millisecond.
Moving on to Section 2, the math of change. Let's look at the equations behind the speed.
So this brings us to the very famous rate law. This elegant little equation expresses the reaction rate in terms of the molar concentrations of the reactants, which are labeled here as A and B. But I want you to notice the exponents x and y. These aren't just random placeholders, they actually represent the sensitivity of the reaction to each specific reactant. If you add them up, you get the overall order of the reaction. But listen, here is the absolute most important thing to remember about this. Those exponents are determined strictly experimentally. No way around it. You absolutely cannot just look at a chemical equation and guess them. You have to physically test it in a lab. Finally, check out K. This is the rate constant. It's the supreme proportionality factor of the whole thing. It doesn't care about concentration at all, but as we're going to see in just a bit, it is highly dependent on temperature.
Because of all this, it is absolutely crucial to distinguish between the order of a reaction and its molecularity. It's a trap a lot of students fall into, but this table breaks it down perfectly. Order, like we literally just saw, is the sum of the powers in that experimental rate law. Because it's strictly derived from messy lab data, it can actually be zero or even a fraction. It applies to the complex overall reaction. Molecularity, on the other hand, is completely theoretical. It is simply the number of colliding species in one single isolated elementary step of a reaction. And since you obviously can't have half of a molecule crashing into something, molecularity can only ever be whole integer values like 1, 2, or 3.
Now let's see how these different reaction orders actually play out over time using what we call integrated rate equations. On the left, a zero-order reaction gives us a perfectly straight, predictable line simply because the rate is entirely independent of the reactant's concentration. It just steadily chugs along. But look at the first-order reaction. Here, the rate depends directly on the concentration. This leads us to one of the most fascinating metrics in all of chemistry, half-life. That's the time required for a reactant to reduce to exactly half of its initial amount. Look at the graphic on the right. Whether you are dropping from your initial concentration down to 50% or from 50% down to 25%, the time it takes to do that, the half-life, is precisely the same. The mind-blowing insight here is that for first-order reactions, the half-life is a constant value, completely independent of how much stuff you actually started with.
Section 3. Variables that control speed. Let's look at the physical levers we can pull.
When it comes down to it, there are three fundamental variables we can control to change reaction speeds in our daily lives. First, the concentration or pressure of the reactants. Second, the temperature of the environment. And third, the presence of a catalyst.
Let's look at these mechanisms right up on the screen. We've got a piston increasing concentration and pressure by physically squeezing particles closer together, a thermometer representing the heat we can add or remove, and a specialized tunnel representing our catalyst. But remember our rate constant, K, from a few minutes ago? While concentration changes the immediate rate just by putting more stuff into the mix, temperature and catalysts actually go in and fundamentally alter the rate constant, K, itself. Honestly, this is exactly why we put our food in the refrigerator. By purposefully lowering the temperature, we drastically slow down the kinetic rate of bacterial growth. Let's look a little closer at exactly how temperature and catalysts perform this magic.
Now, what is really interesting about this slide is seeing that temperature effect visualized through the Arrhenius equation. This graph is plotting the fraction of molecules against their kinetic energy. You see that vertical line? That is the threshold energy, the absolute minimum energy a molecule needs to actually react. The solid blue curve is our starting temperature. Notice how only that tiny blue shaded area represents molecules with enough energy to react? But watch what happens when we raise the temperature by just 10 degrees Celsius. The whole curve flattens out and shifts slightly to the right. That's the orange dashed line. And wow, look at the difference. That slight shift massively increases the area past the energy threshold, pulling all that orange shaded area into the reaction zone. This is exactly why a mere 10-degree rise can nearly double a reaction's rate.
To truly grasp why this happens, we need to talk about activation energy, represented here as EA. I want you to think of activation energy as a massive, exhausting mountain that our chemical reactants are literally forced to climb. As they absorb energy and hike up that reaction coordinate, they finally reach the peak, forming a highly unstable, temporary activated complex. Only after surviving that grueling peak can they tumble down the other side to finally become the stable products we're looking for. So when we add temperature, we are basically giving way more molecules the energetic leg strength they need to hike over that mountain.
But hey, what if we just don't want to hike the mountain at all? Well, that is the absolute genius of a catalyst. Think of a catalyst as your ultimate chemical helper. It doesn't give the molecules more energy to climb. Instead, it provides a completely alternate pathway. It literally digs a tunnel straight through the mountain, which results in a vastly lower activation energy. The starting reactants and the final products remain exactly the same. The overall equilibrium isn't altered even a tiny bit, but the journey to get there becomes vastly easier and so much faster.
Section 4. Microscopic collision theory. Let's shrink down and look at the microscopic geometry.
Developed by Max Troutz and William Lewis, collision theory strips away all the mathy complexity and asks us to imagine reactant molecules as simple, hard little spheres just bouncing wildly around in a box. For them to react, they must physically crash into each other. This introduces a really key variable, Z, or the collision frequency. It simply measures the sheer raw number of physical collisions happening per second per unit volume. This sheer volume of microscopic crashes establishes the absolute baseline potential speed of any chemical reaction.
But guys, this brings us to a really pivotal question, and I want you to genuinely think about this for a second. If a container is filled with billions of molecules, and they're constantly colliding into each other at incredibly high speeds with plenty of energy, why doesn't every single crash result in a reaction? Why doesn't the whole container just react instantaneously the second you mix them? There has to be a missing puzzle piece, right?
Well, the answer is geometry, specifically something called the steric factor, labeled P. It turns out that just having enough energy to climb the mountain isn't enough. The molecules must crash into each other facing the exact right direction. Think of the classic lock and key analogy we've got right here.
In scenario A, the molecules definitely collide, but their orientation is totally wrong. They just bounce harmlessly off each other, no reaction at all. But in scenario B, they approach with the proper alignment. The key fits perfectly into the lock, leading to a truly effective collision and successful product formation.
And finally, Section 5, the master synthesis, bringing it all beautifully together.
Seriously, just look at how beautifully everything aligns on our final equation slide. Up at the top, we have the Arrhenius equation. That's our macroscopic math defining the rate constant K. It features this kind of abstract pre-exponential factor called A. For a long time, A was just an empirical constant that made the math work. But right below it, look at collision theory, our microscopic physics. It reveals that the abstract A isn't magic at all. It is literally precisely equal to P times Z. It's just the physical geometric probability of facing the right way, that's P, multiplied by the sheer frequency of molecular collisions happening every second, which is Z.
And that brilliantly brings us to my absolute favorite thought to leave you with today. When we write an equation on a chalkboard, it isn't just some abstract, boring rule. It is literally translating the chaotic, high-speed dance of billions of microscopic spheres into predictable real-world speed. Mathematical models perfectly mirror microscopic chaos. Very next time you see a log burn or watch a reaction bubble in a beaker, I want you to ask yourself, what invisible microscopic collisions are dictating the speed of that exact moment? Thank you so much for joining me on this explainer. Keep asking those big questions, and I'll see you next time.